following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Example, percent dissociation of a weak acid. What is the percent dissociation of acetic acid when the initial concentration is 1.0 molar, 0.1 molar, and 0.01 molar? And the acid dissociation constant given to us is 1.8 times 10 to the power of negative 5. Okay, great. So the first thing that we're going to do is what we've always been doing here is write down the balanced equation for our dissociation equilibrium. And this time I'll also just show the water, but I'll just put it on the side here, just so we see it. Okay, and then our acetic acid, and that is in a aqueous solution, giving us that, and our acetate ion. Perfect. Our initial concentration is given to us as just 1.0, and we can just go ahead and write that in as well. And then our change now is going to be the amount of the concentration that's going to dissociate, and we just always define that as x, and we're going to gain that here, right? Excuse me. And now the equilibrium concentration therefore becomes 1.0 minus x. This is just going to be x, and this is just going to be x as well. Great. To calculate what we're actually looking for, if we go back one slide now, what we're actually looking for is now just the concentration that dissociated. So that is our x value. We're given this value down here, which is the initial concentration. That's what we're trying to solve for now. We're just trying to get the value of x. And how can we find the value of x? Like we've been finding all this time is through, because we don't have pH this time, because last time we had pH, this time we can find the value of x through the acid dissociation constant. Let's go ahead and do that. For the acid dissociation constant, let's first write down our reaction here. Perfect. And that's just going to be our acetate ion there over our acetic acid concentration, right? And this is just going to be x, and this is just x, and this is going to be 1.0 minus x, and this is all equal to 1.8 times 10 to the power of negative 5. Okay, great. Now, I just want to introduce a quick concept to you guys. Whenever x firstly we make the assumption, but whenever x is less than 5% of the initial concentration, in our example here, we're making the assumption that x is actually going to be less than 5% of the initial concentration, then what we can actually do is we can neglect this amount here, and we can just rewrite our equation as x squared over 1.0, which is equivalent to 1.8 times 10 to the power of negative 5. Now, if we were to go ahead and solve this part, right, and we find that x is actually greater than 5% of the initial concentration, which is 1.0, then our assumption is not justified. However, if we go through this and we find that x is less than 5%, then our assumption is justified and you can take this route. Now let's go ahead and just solve for x. Once you iso x, you get the following: 1.8 times square root of 1.8 times 10 to the power of negative 5, giving us a value of 4.2 times 10 to the power of negative 3. Okay, great. Let me just highlight that because we did write down a lot of stuff. So that is the value of x there. And just looking at it, you can already tell that this is not going to be 5%. This is going to be less than 5% of this. Thus, our assumption is justified. Well, now that we know what x is, right, the concentration that dissociates from our acetic acid here, and we know the initial concentration of the acetic acid, let's actually now go to our next slide, because we're limited for room here, and find the percent dissociation. Okay, great. And for percent dissociation, I'm just going to write down PD. Maybe I'll just put percent in brackets for you guys, just so you understand. And, now we can write it like this. We take the hydronium ion concentration over the acetic acid concentration. And the reason we write it like this is now, because if we go back and we take a look, right, firstly, let's go back to our equation. It's the concentration that dissociates over the initial concentration, and the hydronium ion concentration is the amount that dissociates, right? That's why that's in the numerator, and then this is the initial concentration, that's why that's in the denominator. Perfect. We can go ahead and solve for that, and that is actually, apologies here, this should also be 100. So this is going to be 4.2 times 10 to the power of negative 3 over 1.0. This gives us, and again, this is when the concentration was 1.0, right? That's going to give us a value of 0.42%. When we made that assumption, right, this now for sure is justified, because it's not even 1%. So, right, it's not even 1%. X is not even 1% of the initial concentration. Okay, great. Secondly, what I'm going to do now is I'm going to allow you to calculate it on your own, but when you're looking for the percent dissociation for 0.1 molar solution and a 0.01 molar solution, all you do is at this step here where you have x squared, right, over 1.0, you change the initial concentration here, right, x squared, and you change the initial concentration here, and you start solving from right here for 0.1 molar solution and for the 0.01 molar solution. And once you do that, right, you'll get a value of, let me just write it down here for you, it's going to be 1.3%. You're also going, and then when you do it like this, for the next one, you're going to get a value of 4.2%. Wonderful. And there's something that I want to demonstrate to you guys, and that's why I'm going to allow you to calculate this and just get to my point. Okay, firstly, what we see here is when we go from 1.0 to 0.1 to 0.01, we see that the solution is becoming diluted. And as the solution is becoming more diluted, we're seeing that the percent dissociation is increasing, right? And furthermore, because this is less than 5%, that's why even for the 0.01, our assumption is being justified. Perfect. Just want to introduce that. Just want to reinforce that point to you guys. Now, getting back to what we were just talking about, because our solution is becoming more diluted, our percent dissociation is increasing. And now, if we go back a few slides, right here, we said that primarily for weak acids, percent dissociation increases with increasing dilution, right? And that's exactly what we're seeing here. That as our solution is becoming more diluted, our percent dissociation is increasing. Okay, wonderful. That brings us to the end of that question.